In this class, we're going to consider finding the equation of a tangent to a curve. So not only is this a very typical calculus problem, but this is actually the classic calculus problem. This is the one that really inspired the whole sort of study of calculus like a few hundred years ago. So the scenario here is that we've got some curve, and let's define, say, a point of tangency. So it's just a point where our tangent line is going to touch the curve. And let's say that our tangent line just, skiffs the curve like that, and so just touching at that one single point. So we're basically trying to find the equation of this line. Now, before you learn calculus, you learn that to find the equation of a line, you need effectively 2 points on the line, and you use those 2 points to make the gradient. And then you put those into, usually, well, there's a few different formulas you can use, but one of the formulas would be like y minus b equals mx minus a. And the criteria for using this formula is that you know two things. So you know the gradient, which is m, and you know some point on the line ab. Now, it's generally the case in these questions that the point on the line is going to be given to you because it's going to be the point of tangency, and you kind of need to know that to do these questions, or else it would be some other question types. You'll generally be given that. And in the examples that we're given here, these have both got the full coordinates of that point. This has only got a partial coordinate, but basically that's enough information. We need to know at least one of the coordinates of the point. So you can effectively think that this point is going to be given to you. So the real challenge then with these questions is finding this value, the m value, the gradient. Now, again, before you do calculus, when you're still in sort of pre-calculus, you learn that to find the gradient, you need that second point on the line, like I said. So let's say we had a second point over here, that would be great. But this is calculus, and we do things a little different here. And well, anyway, we don't have a second point on the line. We've only got 1 point. So somehow we've got to work with the curve or the point or both to figure out the gradient of that tangent line. And the way it basically works is, if you imagine that you had another point up here on the curve, and we already actually looked at this way back at the start of this series on calculus, because we defined our derivative actually in this way. So let me just take that out of there in case it causes confusion. So if we did make a sort of little construction line here, using that second point, then we could take the gradient of that line using the 2 points, and that would be sort of an approximation, wouldn't it, to the gradient of this line. So that would be the gradient there, but the gradient we actually want is there. But if you imagine starting to shrink that point back towards our point of tangency, this, remember, is our point of tangency here, so point of tangency. If you shrink that back, and let me just quickly put on another construction line, you can see that that second line is a little shallower than the first one, so it's starting to approach the gradient of the line that we're interested in. If you shrink it back even further, then it would be even closer. It's a little difficult to show in the diagram, but basically as that point shrinks back towards the point of tangency, the gradient of our little lines that we're making starts to approach the gradient of the tangent line. And we said actually, and we're not going to go into it here because we don't have to, but we said when we defined the derivative that if you actually take the limit as you shrink that point all the way back to 0, so the limit as the difference, so I think we defined the difference between these 2 points in terms of their x coordinate as delta x, so the difference between those and x, as you shrink that delta x to 0, so in other words, if you take the limit as the delta x tends to 0, then what you're effectively then doing is turning the gradient of these little construction lines into the gradient of the tangent line. Okay, and that's how we defined our derivative. So basically, when you do this, what you are doing in effect is taking the derivative. In other words, when you take the derivative, now it's a derivative of the curve, right? Not the line. It's a derivative of the curve. When you take the derivative of the curve, you are in effect finding the gradient at that point. But not quite, because when you take a derivative, excuse me, when you take a derivative, you don't find necessarily a number. You find a function, don't you? So if I take the derivative of, for example, this curve here, which would be a parabolic curve, I'm not going to get a number, I'm going to get a function, but the gradient is a number. So how do we tally those two things up? How do you connect what I'm saying is the gradient of the tangent line and the derivative of the curve. I'm kind of saying they're the same thing, but they can't be the same thing because the derivative is usually a function and the gradient is a number. Well, all that it is when you take your derivative, it is a function, but sometimes we refer to it as the gradient function because it is a function that's got x's in it, but you're only ever interested in one point of tangency. So you're always shrinking back to one particular point. So let's say this was some x equals a value. If you then take your gradient function and sub in that a value, then that will then give you a number. And that number is the gradient of the tangent line at that point. So I hope that makes sense. That is a little difficult. It's not an easy concept. But basically, the way to look at it is this. When you take your derivative, that derivative is itself a function. So for example, this guy here, if we take the derivative, so dy dx, now in this problem, we're trying to find the equation of the tangent line to this parabola, this curve, at this point 110. And to do that, we know that we've now got a point, 110, but we need the gradient. If we take our derivative, the derivative comes out to be, using the power rule, 2x plus 3. Now our goal here is to find the gradient, not to find the derivative. The derivative's going to help us find the gradient. This is a function, but this function here is what we call the gradient function. To turn the gradient function into an actual numerical gradient, we just sub in the x coordinate of the point we're interested in. And in fact, this function gives you the gradient at any point around the parabola. So that there would make some kind of parabolic graph. If you wanted to know the gradient of the tangent line at this point, you just sub in the x coordinate of that point. If you wanted to know the gradient of the tangent line at this point, you sub in the x coordinate of that point. That's how it works. That's why calculus is very powerful. So it's turning a process which pre-calculus required 2 points on a line to a single point. We call that an instantaneous rate of change, or an instantaneous gradient, I guess you could almost call it as well. So to turn this into the gradient, the m value, we just sub in 1. So 2 times 1 is 2 plus 3 is 5. So the gradient is going to be 5. Okay, so I've kind of run out of space here, so I'm just going to move my next example over the way. Okay, so this guy here to -6. So we've got our gradient now, and we've got a point on the line, the point of tangency, 110. So we just need to plug those two things into our formula. So we're going to get y minus b, b is 10, equals m, the gradient, x minus a is 1, like this, and then just expand in the bracket to get 5x minus 5, and then putting that into the correct form of a straight line. So y equals 5x, moving the minus 10 over, it becomes a plus 10, so we get 5x plus 5. Okay, so this part is fairly trivial. Just remember, if you're trying to find the equation of any line, in this case a tangent line, you always need these two things, a point on the line and the gradient. It's just that in these questions with calculus and derivatives, we're going to find the gradient using the derivative of the curve. So let's scoot down and have a look at this one actually. So we'll just go through this one a little more quickly. We know what to do now. So we take our derivative, so dy dx. So using the power rule, that's going to be minus 3 minus 2x squared. Sorry, just 2x. So this one's written kind of backwards, this parabola, and that's just because it's got a negative x squared term. Remember, a negative x squared term on a parabola, on a quadratic, means the parabola would be upside down like this. We're not too worried about that. That shouldn't really affect this question. We're not doing anything geometrically. We're not sketching this scenario. We're just working with the algebra and kind of trusting the algebra. We know that we can turn this into the gradient. I can just probably do it here by subbing in this number 2, the x coordinate. So 2 times 2 obviously is 4, so it's going to be minus 3 minus 4, which is negative 7. Then we can just put this all into our formula. So y minus b, our b value is negative 6, so it's going to be y minus minus 6 to give you a y plus 6 equals a gradient, x minus the a value, which is 2. Multiplying out the bracket, minus 7x plus 14, because we've got a double negative there, moving the 6 over, and we get y equals minus 7x, 14 minus 6 gives you plus 8. Okay, so you can go through these really quickly, and like I say, there's no need really to think too much about the geometry. But one interesting thing is that even without really sketching this thing accurately, we know the parabola is upside down. We can see the gradient there is negative 7. That's a very steep negative gradient, that's going to be something like that. That means that the tangent line has to be over here somewhere. It can't be here because it wouldn't be a tangent line. It would have to be cutting through the curve there. So it's maybe like over here somewhere. And we can already start to figure out that geometry just by a real quick inspection of the function and the information we've got there. Okay, cool. Right, so let's take a look at our final example. So in this one here, we've also got a parabola. These have all been parabolas, all quadratic functions, but this works for any type of function. I mean, you could have, for example, like a cubic function like this, and you could maybe have a tangent line going up here, or something like that. These just happen to be parabolas. This one's slightly different in that we've only been given the x coordinate of our sort of point of tangency. We do need both points because we need to sub them in to the formula here, so we need an AB, but all we need to do is sub the -3 into the original function to get the y coordinate, just by sort of pairing those up. So -3 all squared is +9, so it's going to be 8 minus 9, which is -1, so the y coordinate is -1. So our point of tangency here is -3 minus 1. That's quite common actually, to only get the x coordinate. And even though it seems like a fairly trivial thing, it does cause a lot of confusion. So remember, you'll always need the full coordinate of the point of tangency. So you might need to turn your x coordinate into the corresponding y coordinate. So now that we've done that, we can take our derivative. So we'll call that dy dx, derivative of y with respect to x, which is going to be -2x. So fairly straightforward derivative. We can turn that into a gradient just by subbing in the x value of the point of tangency, which is -3. So -2 times -3, double negative, gives you +6. Then we just need to put all the information, the gradient and the point of tangency, into the formula for a straight line. So we get y minus b, so that's y minus -1, which is y plus 1 equals gradient 6x minus a. So the formula is minus a, but a is already minus, so it's minus minus, double negative again. So +3, multiplying out the brackets, we would get y equals 6x plus 18. But if I move the 1 over, that's going to be a -1, so it'll be 18 minus 1, so plus 17. Okay, so the theory behind this is a little tricky, but in these questions, you will never be asked to sort of find the equation of the tangent line from what we would kind of call first principles here. This is more just tying in what we're doing here with the original definition of how we defined a derivative, and this idea of shrinking back to basically the point of tangency to get the equation or the gradient, and therefore the equation of the tangent line. In practice, all you really need to focus on, what I'd like you to focus on most, is that when you take a derivative, you're constructing a gradient function. So that derivative, this guy here, or this guy here, or this guy here, these are the derivative, but they're also the function that gives you the gradient of any tangent line as you move around the curve. To turn it into the gradient, which is a numerical value, you just sub in the point of tangency. So connecting basically the gradient with the derivative, that's really the key takeaway from this class. Like I said, classic problem, this one in calculus. Almost certainly you're going to see this on, assessments or like homework or things like that. So it's definitely a good one to practice and to get comfortable with. And you'll see variations of this problem as well. But this is one to give particular attention to. It's not a difficult process really, but understanding what you're really doing is less straightforward, and it's good to keep in mind this sort of original definition, and it's good to keep in mind as well the kind of geometry. Like you might even want to use a graphing utility as you work these questions so that you can sketch the original curve and sketch the straight line that you get, just to see how the geometry is working. As you move further into calculus, you're going to be doing more problems around the link between derivative, gradient, and sort of the geometry. So it's good to kind of maybe get a sense for that now. So definitely check out a few practice questions using this technique.